Hello, we're ECE Team 2019, and we are working on the wireless motor sensor project. My name is Ben Hart.
I am Daniel Leclerc.
My name is Rasol Talukdar and our faculty advisor is John Chandy.
The project sponsor is the Hartford Steam Boiler Inspection and Insurance Company. To help their customer better manage their risk profile, HSB is interested in developing an Internet of Things sensor that can monitor AC motor working conditions. This data can be further combined with data analytics to monitor efficiency or predict maintenance needs and failures. HSB is specifically interested in an external sensor that can be installed by an unlicensed user like a stick-on sensor.
Here are the expectations that our sponsor would like us to focus on. It needs to be easily installed, sturdy, have a long battery life, and it needs to be able to send data wirelessly. The minimum requirement for this project is to measure motor on or off. Additionally, HSB would like the sensor to measure motor surface temperature, vibration, speed, and loading. The functions in green are the ones we have completed.
Features of our project include our sensing capabilities, long battery life, long-range wireless transmission, online data display, charging capabilities, and universal motor mounting. The dimensions of the enclosure are 3.8 inches by 3.8 inches by 2 inches. It is made of 3D printed PLA plastic. The wireless motor sensor is attached to the motor with adhesive and quarter pipe attachments. The quarter pipes can be custom printed to fit the curvature of the desired motor casing. The sensor system is shown by this block diagram. The device enclosure includes the Arduino, all three of our sensors, and the battery. The sensors collect the desired data from the motor, which is then interpreted by the Arduino. Packets of the data are sent wirelessly to the gateway using LoRaWAN every 20 seconds. The LoRaWAN gateway is linked to the Things network, where received data can be viewed and interpreted.
Here is the sensing and data collection algorithm. First, the local variables are initialized and the sensor connects to the LoRaWAN gateway. Then, the data collection loop starts. Data is collected, processed, and sent to the gateway. After, the sensor enters sleep mode for 20 seconds. After the 20 seconds, the sensor wakes up and starts to loop all over again. In order to determine whether the motor is on or off, the magnetic field sensor needs to be positioned in the tangential position as shown by these diagrams. We are using a linear magnetic Hall sensor for the motor on or off detection, a 3-axis accelerometer for the vibration sensing, and a K-type thermocouple for temperature sensing. The microcontroller that we are using for the wireless motor sensor is the Things Uno that has an integrated LoRaWAN module that can transmit sensor data far distances. To easily interface the sensors with the Things Uno, a shield was designed to fit on top of the microcontroller. The shield is on its second revision shown to the left. The board contains the battery charging circuit, the thermocouple amplifier, the Hall sensor input, and the accelerometer inputs. To get an idea of what it will look like, the first version of the Arduino shield is in the image to the right.
This is the piece of equipment that our sensors connect to using LoRaWAN. This gateway connects to the internet via Ethernet or Wi-Fi and effectively bridges the gap between our sensor nodes and our Internet of Things platform. Spreading factor is an important variable when considering the wireless transmission. By increasing this factor, the overall range of the setup is increased at a cost of lower data rates. The Things network allows their users to integrate different functionalities to their Internet of Things networks. What this means is that we can link an application called ThingSpeak in order to better visualize our data. ThingSpeak uses MATLAB to interpret incoming data and graph it in real time. This allows us to look more easily at how the motor parameters have varied over time and make it far more apparent when an anomaly may rise.
The cost per unit of the wireless motor sensor is $193, which is less than our $200 goal. Our total project development cost is around $570, which is under our $1,000 sponsor budget.
Our test setup is a variable load water pump. The loading can be adjusted with the red ball valve. The motor is controlled by a variable frequency driver, which sets the RPMs of the motor. The motor constantly pumps water from the reservoir to the reservoir in a constant closed loop. Here is the data from a test with the variable frequency drive set to 30 Hz while the data was recorded for 1 minute. As you can see, the motor status is a 1, which means that the sensor detects it is on. The temperature varies but stays around a constant value because of the tolerance of the thermocouple. And the accelerometer data shows that there are small vibrations caused by the load.
Further development of this project would entail replacing the Hall sensor with a coil or attaching a magnet to the motor shaft to more effectively utilize the Hall sensor for loading and speed sensing. Power-saving techniques and PCB designs could also be improved upon. Finally, different enclosure materials should be tested for performance.